So we'll spend a few minutes here just covering activated carbon. Now, I'm sure most people here on this webinar are familiar with activated carbon, maybe not used from an in-situ perspective, but utilized, ex situ. So in carbon vessels on the back end of treatment systems, for example. So, carbon can come from multiple sources. So coal, coconut, wood. Thing that's important to know is that the different sources have different sorption characteristics, and so different sorption capacities, as well as different affinities for different compounds. So, for example, we've tested in our lab different types of carbon, and the coconut carbon did not sorb things like MTBE, as well as coal-based carbon, which is where the BOS 200 and 100 products they're made from. They are coal based, and we didn't mention it, but Calgon Carbon out of the U.S. Manufactures the BOS technologies for RPI. And so, take the carbon; it's either physically or chemically activated to give us that internal surface area. And so there are really three different kind of ranges of pore sizes when we talk about activated carbon. So there's the macro, the meso, and the micro pores. Macro being the largest, obviously, the micro being the smallest, and the meso sort of being in the middle there. And when you get contaminants sorbed into the micro pore structure, those don't move around very much, but in the meso, and especially in the macro pore structure, the contaminants can move around. And we'll talk about here in a minute that contaminants aren't permanently sorbed, and that they can be actually kicked off carbon depending on the situation. Here's a photo that has been in a couple of presentations. This was given at the Patel conference several years ago. And this researcher was just looking at biofilm growth. This was specifically for PCBs in contaminated sediments, but it gives you a nice idea of how bacteria, which is going to be a key part of the treatment mechanism we're going to cover later, how they like to inhabit that pore space, especially the macro and some of the mesopore structure of the activated carbon. And so I'm sure most of you, those of you that have looked at activated carbon and have sized canisters, obviously it's going to be specific to, or the loadings are going to be specific, the amount of carbon you need. It's going to be related to the contaminant itself, the concentration coming in, concentration that you need to have coming out. And so but here is just there's preferential sorption that goes on, and so kind of the higher molecular weight, the more complex the molecule, the higher affinity it has for activated carbon. So a multicyclic PAH is going to stick onto carbon easier and stronger than, say, an aliphatic, or PCE is going to more strongly sorb than something like vinyl chloride. And to actually quantify that, you can look at these charts down below where, just look at the top row. If you've got 10 ppm of benzene, sorption capacity for the carbon is 40 milligrams of benzene per gram of carbon. Using that same concentration for ethyl benzene, it's almost an order of magnitude higher. And so this is why when we do designs, we have to look at the species. It's really important. So we usually have that information, but what we also need is a total mass. So in a hydrocarbon setting, we need to have a good handle on how much benzene is there versus how much toluene versus xylene. But we also need to know what's that total gasoline range organic value. What's the same thing with diesel range, for example. So we need kind of both, but we look at the individual constituents because the sorption isotherm coefficients are different for each contaminant. I'm also, wanted to make a point about rollover, which is what in the activated carbon world, what they call when a contaminant gets kicked off. And I alluded to that a few minutes ago. So here was just a really simple experiment that was done at RPI, and I'll walk you through it. So we had 2,000 ppm of xylene that was added to BOS tubing, and the equilibrium concentration was 1.42 ppm after everything stabilized and equilibrated. And the second vial, they took 100 ppm of vinyl chloride and did the same thing, let it equilibrate. We had 2.42 ppm of vinyl chloride left in the aqueous phase. They took that second vial that had the vinyl chloride and they spiked in that same 2,000 ppm of xylene that we had in that first vial. And you can see at 1 hour and 24 hours, you can see how the vinyl chloride value is increasing over time and that xylene concentration is decreasing over time. And so when we talk about preferential sorption, you know, it's especially when you have a site that's got mixed contaminants, we have to be able to account for this in the design. And it's something that's important when you, for something like, I don't know, if you're looking at activated carbon for something that really doesn't stick on the carbon well, like vinyl chloride fits into that, 1,4-dioxane fits into that, PFAS, PFOS kind of fit into that same category. Those things can be sorbed, but they can be ultimately desorbed. Okay, so we'll wrap up the carbon part and talk about what we call this trap and treat concept. So the trap part is easy. That's the activated carbon. We've already sort of covered that. So how do we leverage that activated carbon in the subsurface? So we use this technology in really two main applications. One is going to be reactive barrier walls. So we're trying to just limit mass flux. So we've got a property boundary or we've got a sensitive feature, a stream or a wetlands that we're trying to limit the mass flux of our contaminants moving in there. And most of the time when we do those applications, we're downgrading to the source. So we're dealing mainly with just aqueous phase mass or hydrocarbons in the case of today's conversation. And so in that case, that activated carbon is acting almost the same way that it is in those ex situ carbon vessels. Okay, as it's fluxing through that cross section, the activated carbon is going to sorb onto the activated carbon, and then we'll get to the treatment here in a minute. But in source areas, it's a little more complex because if you look at a total mass in a cubic meter that in a source area for a hydrocarbon site, you might have 80 to 90% of that mass in the sorb phase and not in the aqueous phase. So how do you treat sorb phase? Because it's all the technology you apply in the subsurface. So activated carbon, chemical oxidants, they all work in the aqueous phase. We can't go after the soil directly. So how do you get the mass off the soil into the groundwater so that it can be treated? And so what the carbon does is kind of sorb what's available, and what's available is what's in groundwater. Now you've disrupted the natural soil to groundwater equilibrium that exists. And now you're going to get the system is going to reestablish equilibrium. So things are going to the hydrocarbons are going to start to desorb off the sorb phase into groundwater. So those of you that are familiar with chemical oxidation, that's what rebound is. So you get, you oxidize what's in groundwater. Most oxidants are good for, maybe a couple of weeks to a month. Once it's not active anymore, you get rebound. That's what that is. That's that system re-equilibration. And so when we do designs for our products, we're looking at total mass in the system. The one caveat there is that we can't control that diffusion rate, and not all contaminants are going to easily come off. So if you've got a diesel range source area, that can be hard to desorb. But we can give those recommendations if we have the information to be able to say, hey, it might make sense to either use another technology or maybe maybe we excavate this, and maybe in another part of the site, this technology makes sense. So it is, it's going to be a function of the fraction organic carbon of the soil. So it's going to be tied to the soil type, as well as the contaminants themselves, as to how much we feel we can actually back diffuse out of soil into groundwater. And then when it comes to the actual treatment mechanisms, and we'll look at this a little more closely on the next slide, but we're going to focus on bio today. So we're going to add bacteria electron acceptors in with the activated carbon to be able to biodegrade the contaminants that are sorbed to the activated carbon. The other technologies are a little different. BOS 100, which we're not going to really cover here today. The degradation chemistry is very similar to zero valent iron. So those of you that are familiar with zero valent iron chemistry, it's very similar to that. And then CAT 100, which is essentially just a modified BOS 100. It's a BOS 100 with a enhanced reductive dechlorination, or ERD, component to it. So again, if you're interested in those technologies, we're not going to cover him here today. To check out the webinar that I had linked to before, or give us a shout offline and we can go ahead and set something up. And one of the other comments that I'll make about activated carbon when you're using bio is that you can vary the dosages of the carbon depending on what your goals are and budget as well, because you can rely more on the upfront carbon adsorption, or we can rely less on that, less carbon, more bio. So we can add more bio amendments, less carbon. Now that's going to give you a longer treatment profile, but there's a lot of flexibility with our design options. Okay, so most of our projects are going to be either hydrocarbons or chlorinateds. Again, we're going to focus on the hydrocarbons today. It's got a pretty wide applicability range, and so there's an upper limit, obviously, to every technology, but we can get into some concentrations. If you have 2, 3, 4,000 milligrams per kilogram total mass, total hydrocarbon mass in soil, that's a range that we're comfortable working in, which is typically the NAPL range. Now, we have to evaluate those closely. If you have a site that you've got a sample that's got 10,000, 15,000 milligrams per kilogram, it's doable, but you might be looking at multiple applications. And so typically source treatment, we're looking at either direct push injections, which is what we'll cover here today mainly, or as with any other technology, you can do some soil blending, or you can do a combination of the two. So if you are doing some excavation, the best way to get any amendment applied to the subsurface is with in-situ mixing, because you'll never get better distribution than mixing it in with either a mixing head or a bucket. And then maybe we're doing injections below that or down gradients. We do quite a bit of sort of combined remedy approaches with these technologies. For plume treatment, you can obviously expand that source area out to include the whole plume, but there's a limit to where the economics just don't make sense. So we will typically flip that over and look at, maybe you're doing some focused source treatment, but then you're doing some down gradient reactive barrier walls. And that seems to be the most cost-effective combination of approaches for most sites. And we do a lot of sites where we're just doing a PRB. Maybe there's an existing mechanical system, maybe everything was dug up, and the goal of the project is to just install a reactive barrier wall. And that can be done with either injections, or if it's shallow enough, we can go ahead and trench the material in. And so we can skip down to that fourth slide. The first three we've really covered already, but the third slide from an applicability range. And so from an overburden geology standpoint, based on the maps that we showed you earlier, we work in around everywhere in the U.S. and in countries around the world. And so we're working in both fine grain and coarse grain soils. those are usually done with direct push. Again, that'll be kind of the focus for today. We're not going to cover bedrock. That's done. Competent bedrock injections, which we do, are done with inflatable straddle packers. And lastly, that pre-drill technique, which I have a breakout slide on that we'll talk about that separately. And that's really for sites that have shallow direct push refusal, but it's not competent bedrock. So it's not going to hold a packer, but you can't get there with direct push. So what are your options? And I wanted to include that in this presentation today, because since we've numerous sites that we've evaluated in Australia are looking like there might be fit that pre-drill category. So here are the technologies themselves. I'll just briefly cover the top two. So BOS 100 is activated carbon that's impregnated with metallic iron. So again, it's very similar to zerovalent iron chemistry. It's an abiotic beta elimination pathway. What that means is that you're not generating daughter products like you do with other technologies where you're using enhanced reductive dechlorination. So you're not generating, say, vinyl chloride, for example, which is important from a vapor intrusion standpoint, for example. Because it's an abiotic pathway, we get some good longevity in the subsurface, demonstrated 7+ years, theoretically 10+, similar to zerovalent iron. And CAT 100 is just BOS 100 with an reductive dechlorination component. So we use this for really DNAPL areas, or if we've got mixed contaminant sites. So not everything degrades with iron. So if you've got a PCE plume that's commingled with, say, a chlorobenzene plume, the chlorobenzene is not going to degrade with zerovalent iron. So we can add electron donors and bacteria to that technology, or to the BOS 100 technology to give us CAT. So, but the bottom, BOS 200, that's the focus for today. So in this picture here on the right, as you can see, this is how the material is delivered. It's in 50-pound bags. So, and so it's primarily, again, for petroleum hydrocarbons. Besides the carbon, we're adding electron acceptors. So sulfate and nitrate are our two primary electron acceptors. If there is oxygen in the subsurface, the bacteria that we add, they're facultative. They can actually utilize the oxygen. Most source areas are already anaerobic. But we add sulfate, nitrate, we add micro and macronutrients, as well as a consortium of bacteria. And that bacteria is approved for import into Australia. Okay. So now we'll talk about the proof of concept for the treat part. I think most people intuitively get the trap part, but this is where we get most of our questions, is the proof of concept for the treat. And so everything's always easier on the lab end. And so we can do mass balance experiments. The next slide, actually, I'll show you some data from some tests that we've run at the RPI lab. But once things are in the subsurface, it gets a little trickier with hydrocarbons because you don't really have true daughter products. There's a lot of secondary lines of evidence. So we can look at things like total mass reduction. So total mass in, total mass out for a project. So we go out and do our soil and groundwater survey before the project to dial in our design. And then we can come back at some period of time in the future and just replicate that effort and look at the mass reductions. And the mass reductions are greater than the amount of mass that could be theoretically adsorbed onto the carbon. So if you were to take that mass, and let's just say we've got an 80% reduction in mass, well, we can run the math and say, well, only 20% of that could have theoretically been sorbed onto the carbon, because obviously the carbon has a finite sorption capacity. So we look at soil and groundwater. We can also look at just long-term groundwater data for sites where that have been monitored for many, many years. With chlorinated solvents, it's always a little easier. We can look at dissolved gases. So we can look at things like CO2, methane for hydrocarbon sites as sort of a secondary line of evidence for the biological activity. Chlorinated solvents are nice because we can actually get true daughter products. The last two bullets are things are techniques that have been, I would say the last 5-10 years are starting to gain momentum. So using microbial diagnostics, so sampling the groundwater for bacteria over time. And you can do some pretty cool stuff now with metagenomic testing to be able to see exactly what's there and how that trends over time. Compound-specific isotope analysis is also a really nice way for us to be able to prove the technology is working. So that works on the, there's so much C13 naturally in the subsurface and bacteria preferentially. So if there's so much of, say, your benzene in the subsurface has a C13 on it, and bacteria preferentially degrade the C12 over the C13. So if you get an accumulation of C13 over time, that's a line of evidence for degradation, and that number wouldn't shift if we were looking at just adsorption. So that, if you're not familiar with that technique, I can, point you to some labs that focus on that. They'll give you a much better description probably than what I just gave you. So the site here on the right, this is a site in Europe that Duane's familiar with. So this is some soil data pre and post application. So the one thing that I'll point to is that time frame down at the bottom. So we're looking at about a 3.5 year time frame. And so when we talked about desorbing mass off of soil into groundwater, that takes time. And that's sort of the scale, especially on a site like this where there was a lot of mass, there was some NAPL. That's the sort of time frame that you're looking at with this technology. But you can see the red was our baseline benzene in soil. Blue was our 3.5 year sample, and you can see that we got significant reductions. Really, only one significant hit out of, and each of those dots is obviously a soil sample. This is that same site actually, and this is the groundwater for that site. And so this is benzene in milligrams per liter. And so again, you can look at the time frame here. So we're looking at 5 years of groundwater data. And here's an example. So this is a chlorinated site. Most of the microbial diagnostics work that we do so far has been on chlorinated sites. But this is a site where we applied the CAT technology and we were tracking bacteria over time. We're looking to do more of this on hydrocarbon sites. Okay, so this is when I referenced the mass balance experiments that we do in the laboratory. This is that slide that I was. This is the slide that I was referring to. So we took a 500 milligram per liter spike of gasoline, and these were the resulting concentration. So similar to what we would see in a typical source area on like a UST site. And so this was mixed with BOS 200, and it was mixed such that we knew we wanted to have an excess. So we didn't want to sorb everything. We wanted to have an excess. So we dosed it so that we had this balance at 3 days. This is what's left in groundwater or in the aqueous phase. The balance of it is adsorbed onto the carbon. Here are your percent reductions. Now, and this is pretty typical what we see in the field after we go and do an application of BOS 200. But this is really only part of the story, right? So this is just the sorption part. This is just the trap part. The bacteria, haven't kicked in yet. And it's also, you also see here how the benzene didn't adsorb as well as the TEX compounds. They have a substitution, so these are gonna sorb better to activated carbon than benzene. But they ran it after 30 days and 120 days, and at each of those times they killed a set of bottles and analyzed what was remaining in the aqueous phase, and then extracted everything off the activated carbon to do a mass balance to see what was left. And so you'll see at 30 and 120 days, here are the percent reductions for the various BTEX compounds. So at 120 days, we had 78 to 95% reductions. And so this is a clear line of evidence that the bacteria are degrading what's sorbed into the activated carbon matrix. So we are going to move into sort of the application portion of the webinar today. So I guess if there are any questions, if you want to throw those in the chat, we can field those on what we've covered thus far.
If anybody's adding any questions, I'll just kind of chime in here a little bit just to summarize what Mike said, and just a quick two-minute kind of synopsis is that, so the carbon serves as the platform for the treatment. And so what we're trying to do when we inject the BOS 200 products in the formation, we're trying to promote back diffusion. Like Mike says, most of the sites, the mass is tied up in the saturated soil. So we're trying to actually promote back diffusion in order to be able to drive the contamination off of the saturated soils into the groundwater onto the carbon. But ultimately, the success of the use of these products is the overall treatment mechanism itself. So if you don't have a treatment mechanism in place on the activated carbon, like Mike says, then what's going to happen is the carbon's going to fill up, and either your site is going to reach some kind of plateau, and you have the potential over time for that mass to desorb off of the carbon. So that's why it's so important to understand that you have a treatment mechanism in place in order to be able to clean up the contaminant mass that absorbs onto the carbon, so that you can free up new sites to be able to absorb mass that continues to back diffuse off of the soils. And so ultimately, the success of the product is driven by longevity. So once you inject these products into the formation, like Mike says, when you're dealing with sites that have significant mass, LNAPL, triple digit, ppm type concentration, TPH, you have to put something in the formation that's going to be able to handle that mass as it comes off, but you have to be able to treat it to continue that cyclical process. So in other words, what you're trying to do is promote natural source zone depletion and end up reducing the cycle of the natural processes that are occurring at the site by providing this platform of the activated carbon to be able to absorb mass, and then to promote actual biological treatment to make it more healthy and hardy because of the total mass that's present within the carbon.
Yeah, we haven't, Mike, we haven't got any questions come through yet. Everyone's either very shy or you're just doing an amazing job, one of the two. But yeah, there's no questions at the moment. But yeah, so we might kick on.
All right, thank you. Okay, so now we'll talk about high density conceptual site model development. And this is, really, this is how we build up our designs. And a lot of sites have sufficient data sets, groundwater and soil. But a lot of sites that we review, the data is either limited or old or both. And so, and I like to say everything works in a beaker, right? So in a laboratory setting, all these technologies that are available, they all work. Maybe some outliers out there if you've got a, extremely low or high natural pH, for example, but in general, everything works in the beaker. So, when things get to the field, we're not all, no one has a perfect record. Why is that? And a lot of the times it's really comes down to two things. We're talking about source areas specifically. One is that contaminant mass distribution is going to be complex. And I like to say that it scales with the heterogeneity of the lithology. And I'll actually show you a site here in a minute. Some data from an actual site that does a good job of really showing how heterogeneous the soil mass can be distributed. And then secondly, talking about contact and distribution of these, because this is, these are slurries. They're not liquids. And so they can be challenging to inject, which kind of gets back to one of my first slides about making sure you've got the right people and the right equipment in the field. And especially when talking about low permeability storage zones, they can be difficult to target. So if you're trying to use injection wells or other techniques, those can be a challenge. So we'll talk about each of these here for a few minutes. So we kind of broke this out just because we've been working with Numac and trying to figure out how we can take this model that we use here in the U.S. and be able to offer it in Australia cost effectively. But let me fill you in on what we do here first, and it's really revolves around that laboratory that I mentioned early on, the project support lab that's based in Denver. And so this RDC process is really taking a fresh set of eyes to your site and using supplemental sampling, soil and groundwater, maybe bringing in high-res tools, maybe bringing in tools like DAMIP, the HPT, UVOS, the technologies that Numac has, combine that with high-density sampling to be able to fine-tune that conceptual site model. And so we're talking about sampling. We're sampling every half a meter, for example. Nested groundwater wells. So if we've got a really long groundwater screen, maybe we're breaking that down vertically as well. And we can send all those samples here, and our partner in Europe, sends most of their samples to us. We're trying to figure out if we can do that cost effectively from Australia, but they send them to RPI and they're run pro bono. So they don't charge for the analyses. And so it's all the same methods, at least EPA methods here for the US, looking at GC mass spec methods, for example, to look at contaminants and also getting things like individual constituents as well as total hydrocarbons present in soil and groundwater. And so here's an example of a site of mine that's up in the Pacific Northwest, where our partner up there advanced 10 soil borings, collected 90 soil samples in one day. That all came to RPI, and this was a carbon tetrachloride site. You see the former grain elevator there, but it really changed the conceptual site model for the site. You can see these different colored blocks that you see in here. These were the different treatment areas, and so we were able to take that site and really break it down into different treatment areas and different treatment intervals vertically as well. And so this is a really large site that we worked on. Not all our sites are large. Our average site is, a UST corner gas station. But this was a larger site, and our client, we went out and advanced a bunch of soil borings, and they actually created a model. So each of those spheres that you see, each of those vertical lines is a soil boring. Each of those spheres is a soil sample. And so they were able to generate a quantitative 3D model, and then this, ultimately becomes your roadmap for your remediation, whether that's, maybe you're doing some combined remedies that this is shallow, this is accessible, let's dig this up, we're going to inject this, we're going to put a mechanical system here. So you can make a lot of decisions when you have this level of information. And so here's how this is a site. Actually, we'll highlight this later. This is a site in Finland where went through that process. Now this is a big UST site. This is not our average UST site. There's a lot of injection points. But you see all the different sub areas here. Each of these has different loadings associated with it, and it's broken down vertically as well. So you might have a shallow, intermediate, deep loadings So they might vary with depth again, depending on where the mass is located. And we're looking at options now to be able to provide this service cost effectively. So the first and sort of the most obvious place for us to start is to work with Numac and their high-res tools to be able to get out to your sites and you know, advance the MIP, HPT, UVOS, as I mentioned before, and combine that with strategic sampling to be able to and with assuming those samples stay within Australia and go to a lab there. Also, you know, here's just a couple other options. Maybe we can identify a lab that can, maybe a treatability type lab that, you know, these samples aren't for compliance. And so is there a laboratory that we can identify that can run these cost effectively for us? Or are there quantitative field screening tools that are out there? So these are options that we're exploring. If you have comments, please throw them in the chat if you've got any comments for us or any insight as to sort of how we can make this happen, because it's really important. And I'll show you a slide here where on most sites the cost for this effort ends up reducing the overall remediation cost, because it's going to tighten up your injection footprint. Maybe it expands a little bit, but the footprint is usually pretty much dialed in with monitoring wells. It's really that vertical interval that changes. So here's, I'll actually show you an example here in a slide or two. This is diesel and soil data from a site here in the US. This is all in milligrams per kilogram diesel and soil. And you can notice a few things. So here's your high and low groundwater table. These are depth in feet. I apologize, didn't miss this one, didn't convert it over to meters. But you get the idea, right? So here's our smear zone. And so here's our sort of, kind of shaded from green to red, our low, medium, and high concentrations. And you'll notice there are some outliers, like this guy right here. That's 6% diesel, and 6% diesel in soil. So there's no technology that can deal with that. It's just way too much mass. If you run the mass calcs on oxidation, or we do it for carbon, it's just you can't put enough material in the ground. And so you have to look at alternatives. Either you isolate this by maybe trying to limit the flux out of this particular area, maybe you dig it up. I don't even think something like surfactants would be applicable for those sorts of concentrations. So it really helps you define where you can and can't work, because again, every technology has a box it fits in. I think that's why that's another reason why sites fail, is that people try to stretch the boundaries of that box for individual technologies. Another thing I'll point out here is this SB21 boring. You'll see, how many orders of magnitude get spanned there with 7 feet. So take 2 meter span, we've got multiple orders of magnitude swing. So this helps us dial in and optimize our reagent loadings vertically with depth as well. And this is a site where actually the footprint grew a little bit once we did the supplemental sampling. It went from 50 to 60 square meters. But really, if you look at the treatment thickness, that's really where we were able to optimize the project. Is that initial preliminary design was based on the total well screen. So the well screen went down to 6 meters. So we didn't know really where the mass was until we went out and did some profiling. And we were able to really narrow that down to 1.5 to 3.7 meters. And so the amount of BOS required came down, the field days came down. Those project dollars are in US dollars, but you can see we had about a 21% savings over our preliminary design, and that's including the RDC cost in there. So I would say this is pretty typical for us, that we see, I would say, 15 to 30% savings on most sites where we go through this process on the front end. Okay, we'll talk about applications now. So this is the other piece, right? So now we have our conceptual site model dialed in. Now how do we get the stuff in the subsurface? All right, so most of our applications we're gonna talk about here are gonna be direct push. And so from clays and silts, sands and gravels, we work in all of those. What's gonna change might be your injection point spacing, maybe the injection points itself, the volumes per injection interval. Those are sort of the variables that we play with depending on the lithology. So something like a clay site might be, that's going to be on the lower volume end for us from an injection standpoint. To something that's a sand and gravel, it's got a lot more pore space to fill. So you may actually have a doubling of that volume per interval going from a clay site to a gravel if everything stays the same. So that pre-drill technique that I had sort of plugged earlier on. And so that's really where these sites where we have refusal, with shallow direct push refusal, we can't get down to our total depth, but again, you're not at competent rock yet. And so it's utilizing, sonic or auger, so traditional drilling methods to pre-clear that hole. So that's the pre-drill. So if we're trying to get down to 10 meters, we have refusal at 5. We're going to pre-drill all the way down to that 10-meter mark. We're going to backfill that with bentonite. We're going to hydrate it really well. It's really a key part of the whole process is that bentonite hydration, get a good seal, and then now we can go back down with direct push. So go back down that borehole, and so you can think about what comes out of these injection tips. It looks like a pressure washer, and so it slices through that bentonite and gets out into the native material. So here, we've used it for a variety of situations, whether it's weathered units, glacial till, which is an issue in say Northeast US, Pacific Northwest, Scandinavia, for example. Or it could just be fill material. There's sites where we just can't do the historic fill. We just can't get through, and so we can use this. So we can use this technique. Bedrock, again, we're not going to cover today. That's using straddle packers to isolate fractures. We do that bottom up. Those of you that are looking at top down, and then you see bottom up. These packers are kind of expensive, and so if you inject top down with a packer and you dislodge something and it falls on top of the packer, you might not get that back. So we do progress those bottom up. And lastly, the soil mixing, which we already covered. So this is an AST setup. I don't know a UST site. Got your geoprobe, got your direct push unit, got your injection trailer. There's your BOS in the back. Pretty small footprint. This is that pre-drill method. So Numac obviously has sonic capabilities, so they'd be able to come out and advance those in before we actually bring the direct push unit out to start the injection phase of the work. For that hydration, I would say the sweet spot we found is 24-48 hours. Once you get past that mark, you should be able to keep a good annular seal. Here's just a shot of the packers that we use. So the packers that you see on the left, we're able to isolate about a 1/2 meter section, so we can really isolate fractures and inflate the straddle packers on either side and pressurize that fracture to get the material out. And then lastly, here's a photo of our first application of the technology in Australia. It was not an injection application that was looked at. However, they were going to be doing some surgical excavations, and so it was ultimately decided to apply the BOS in that manner. And so it was added as part of the backfill. So the contaminated soil was excavated out, and the BOS 200 was added as part of the backfill. Okay. So, when we get to the actual field and we're laying out these designs, and we use really two formats, either grid-based or a PRB. And so we use what we call a triangular grid pattern. So here's your monitoring well, and groundwater is moving up the slide here. And so we like to lay our injection grids out in this pattern to be able to make sure we don't have any channeling of the contaminants through our grid. If you did this on a square, these IMP points, we like to install sacrificial implants whenever we can. Really helps us track the distribution of the product in the subsurface. So a lot of times we've got monitoring wells that have long screens. We can set these implants, and they're sacrificial. They're just there. Maybe you're using those for some of that upfront sampling work. You keep them in, and then we use them to assess distribution when we get to the field phase, especially on any sort of pilot test. And then these can be pulled out. The injection point spacing is going to be typically 1.5 to 3 meters for most sites. It might be a little tighter than other sites and what you're used to. We are injecting slurries, and so we can control that injection energy when it's relatively close to that injection tip. But then once that energy dissipates, it starts to take the path of least resistance. And so as your spacing widens, your injection volume has to increase to be able to meet that radius of influence. And especially on, say, UST sites, for example, that have had a lot of work, they've had excavations, they've got pipe runs, they've got utilities that are shallow. What we've had success with is tight spacing, low volumes, and that way we can keep that material in that theoretical radius, and limit the amount of material that actually comes to the surface, which is going to happen, but it helps us limit that. The other approach that we use often is setting up reactive barrier walls. And so if we could, on every site, we could set up a trench. This is a site where we excavated down to bedrock. We backfilled with a sand BOS blend up to about a meter below grade. As you can see, we're working in the woods. There was nothing around. There were no utilities. It's easy to do. But most sites aren't that simple. We have to use injection techniques. And so what we've had success with is multiple rows, usually 3 to 4 rows of points, tightly spaced, so 1.5 to 2 meters, say. And it's because you're trying to install the material to get you, be able to place this in the field, but using injection techniques. And in our experience, when that spacing widens, or when you only do 1 or 2 injection points, you've got a lot of gaps in that cross section. So using 3 or 4 rows of points, we've gone as high as 5. On some sites, it's going to depend on the mass flux. So calculations are a little different for a source area application versus a barrier, because barriers are going to be designed on aqueous mass flux moving through that cross section. So based on your groundwater flow, your gradient, and your concentration, we can calculate out how much material that we need to put in that cross section. And to be able to get that material properly distributed to give us to a good net, a good flow net. This is the design that we've had the most success with so far. One thing to note is that if you're doing a biobarrier, which BOS 200 falls into that category, we've got to keep those bacteria happy long term, right? And so they need electron acceptors, they need nutrients. The hydrocarbons usually aren't the issue. And so you may need to convert some of these wells, some of these direct push points, say, into injection wells, to be able to periodically, say every couple of years, come in and sort of supplement that barrier. All right, so here's just one slide that's on that pre-drill method that I've that I've already referred to. You know, I think I've covered most of this already. We've done somewhere between 40 and 45 sites using this technique in various issues. One of the case studies, the project summaries I'm going to show you here at the end is actually one of these sites where we use this pre-drill method. Okay, so we'll talk about just liquid versus slurry injections, because this is another sort of a line of questions that we get quite a bit. I think most folks are familiar with liquids versus solids. And so we'll just talk about ISCO. So, you know, before I came here to AST, most of my work was chemical oxidation. It's great, it works, but it's got limitations from a soil oxidant demand. So you got a high organic carbon loading in that soil, or if it's relatively if it's a low permeability soil, where if you got a clay or a silt, for example, it's really hard to get an oxidant to diffuse into that, because again, oxidants are usually applied low pressure, low flow. It can be challenging. And so you can use injection wells or long DPT screens, you know, those are typically used. But again, if the mass is tied up in the low K zones, it's going to be hard. You're looking at many applications. And so this figure on the right is a site that I'm currently evaluating. And so there was some excavation work done shallow, but most of the mass is tied up in these siltier zones. And here's a pretty coarse sand. That's pretty clean, which makes sense. This is a little down gradient, slightly down gradient of the source, but over time, most of the mass is sorbed into these finer grained lenses. So you come in with an injection well, you know, and you span these multiple units in this varying geology. All your liquid's going to go into the sand. That's not where the mass is. And so I think this is a situation. This is a place where I ended up going from chemical oxidation and looking at activated carbon technologies 7-8 years ago, was for situations like this, where oxidants just didn't make sense. And so I was looking for something that I can inject and inject under pressure and be able to force it into these fine grained units to be able to ultimately desorb the mass, like we discussed earlier. So slurry injections, you are going to be using higher flow rates, higher pressures. Injection wells can't be used. So typically we're going to be using those injection tips that are more you know, focused, where all of the injection ports are in, say, one plane. We're not talking about a 1 foot or half meter, 1 meter screen, or, you know, the longer screens that you see used for some of these other liquid-based chemistries. This is a really focused injection. And so here's an example. This is busy, I know. I'll break it down for you. But this is a site that I got involved in a couple years ago, where there was another technology was used. There was no upfront sampling work. They were relying on the existing data set, and they tried to low flow, low pressure this material into a pretty tight formation. This was a PRB, and they had really a limited number of injection locations and intervals. I think they had 1 row of injection points. They were injecting vertically about every meter or so. And they actually did 3 rounds of injections of various things. And this is your total BTEX here. And so you can see a lot of confusing data, right? It was all it's all over the place. You have some decreases, some increases, lots of noise. We move out to this time frame period here. This is where BOS 200 was applied. After we had done some supplemental sampling, it was probably a half day of work. But this was a higher flow, higher pressure application into that tight formation. And we had over 3 times the number of injection points, and we had over 3 times the number of vertical intervals. And so I think it was overall a better PRB design, and was dosed properly. I think the first couple of rounds that were done really weren't dosed properly, and I think they had a poor application. We can, I do see some questions that have come in. I don't know if you, Matt or Duane, you guys want to kind of start fielding those, and then after this, we've got some project summaries, and then let you guys go.
Yeah, sure. Thanks, Mike. So we have had a couple come through. Are there any issues due to groundwater backing up due to the potential hindrance from the RPB reducing the groundwater flow velocity?
No, that's a great question. The only time that I've seen that be an issue on any site that I've been involved in was not an injection approach. It was actually using large diameter augers, and they had used large diameter augers to blend in material over a pretty deep cross section, and the resulting product or the resulting material had a lower conductivity than the native material. So they actually did get some bypass. So if you are looking at soil mixing techniques, I think that's really critical. You want to make sure that your barrier is always more conductive than the native material. But from an injection side, no, we haven't, and that's something that a lot of our clients will install monitoring wells on the wings, maybe even nest a well below our barrier to see if we are getting any sort of, bypass. And then if you look at a design, which we really haven't gotten into, it's a really low percentage pore volume that we're actually applying into that subsurface. So I would say it's usually less than 5% total pore volume. And if you look at the total material that goes in, so obviously some of that's water. So BOS is a solid, we're mixing with water. But once that solid slurry is in place, it's a pretty low percentage of the overall. We're not adding enough material to be able to influence the hydraulics of the site.
Yeah, I was going to say, Mike, that the maximum in most cases is probably 1% by weight of the material to the weight of the formation. So you're talking about 0.05 to 0.22 kilograms, of mass, in a cubic meter. It's really small. Yeah. So the potential for backing up or clogging up the formation it's just not going to happen.
Okay, thanks, guys. The next one is one that's actually come up a couple of times in chats with clients recently, and that's about the impact of the BOS 200 injected near groundwater monitoring wells that would be sampled for hydrocarbon fractions to confirm effectiveness of treatment.
So sorry if I'm trying to understand the question. Is it about water quality?
This is about the effect of that the injection can have on groundwater wells, and then I guess sampling from those wells post injection.
Yeah. So I mean, you're not gonna damage the well. So if it's from a physical, from the actual injection process or just from a chemical standpoint, you're not gonna damage the well. But the wells are within the field of play when it comes to the injections, and so you can get the injectates, in the wells themselves. And so what we've developed is, really just you're going to go in and redevelop the well, and after you finish either a sub area out on a given site or maybe at the end of the project, go in and build in a little bit of time, maybe a half a day, to go in and actually redevelop the wells, to be able to make sure that there's no BOS material that's actually in that's in the well itself. And then from like a water quality standpoint, you know, the only things that you're going to detect are going to be that sulfate and nitrate, and those will deplete over time. So from a sulfate standpoint, you're not going to have concentrations higher than if you're doing an activated persulfate injection. They're probably going to be fairly similar. Those obviously deplete over time. Nitrate is it's more beneficial, or it's a bacteria get higher energy, more energy out of using nitrate. You know, it's further up that ORP ladder than sulfate. That usually only persists for maybe say 3 to 4 months, and then that's gone, or it's at very low concentrations, and then you get into the sulfate reducing range. And so that sulfate will be elevated for typically 18 to 24 months. That's our long-term thermal electron acceptor. So I hope that answers the question. I tried to kind of cover that on a couple different fronts. Duane, I don't know if you want to comment on that as well.
No, I mean, I think Mike covered it. I mean, we have a step-by-step process that's, you know, goes from just purging a well to eliminate the presence of carbon within the well itself to, you know, surging a well with surge blocks to redevelop it, you know, kind of manually. And then it moves in, and if, you know, it continues to persist, then it moves into a process where, you know, you potentially could, you know, bring a back truck with a jetter wand, you know, to actually truly agitate, you know, the sand pack of the formation. But in most cases, you know, we've been very successful in being able to rehab the wells if carbon, you know, enters the well itself. I mean, the point is we do not want to bias any groundwater data, you know, based upon carbon being within the well. So if it's not possible to actually rehab the well itself to the point where carbon is not present in the sample collected from the well, then, you know, our suggestion is to you know, to over drill the well and replace it. But I'm going to say it's very rare that that's the case, that has to happen. If we follow these methodologies that we have in place, then we're able to successfully rehab the well itself.
Thanks for that, guys. I've got a couple of questions here I might be able to tie in. But there's a couple of questions around using BOS 200 after there's been some other kind of amendment applied, whether it's an ISCO or potentially the other one that's mentioned here is an ORC compound on the site. Is, you know, implications for applying it post one of those events?
Yeah, ORC is not going to be a problem. You know, those are either calcium or magnesium based, and if any that is, you know, you could theoretically add ORC compounds to BOS 200 if you wanted to. ORC compounds tend to be relatively expensive, and oxygen isn't very soluble. So we, you know, that's why we really like nitrate and sulfate for thermal electron acceptors. But you could theoretically add it. On the ISCO side, that's a little more complicated of an answer. It's going to depend on the oxidant that's used. So the ones that we would want to look at closely would be if you're using activated persulfate, and then which activator are you using. So if you're using the caustic, like sodium hydroxide activation, you know, that ideally is in pH 11.5 to 12 or higher. And so since we're using bacteria here, we'd want to make sure that the pH came down to circumneutral. So I'd say in the 8 range or lower. If you went the other way and you used hydrogen peroxide or the iron EDTA activation, you're going to have a very acidic pH because you don't have the base to balance out the sulfuric acid. And so in that case, it's the opposite side, right? Now you're talking about a pH 1, 2, 3 injectate that's going into the subsurface. Same thing. We want to get that to be into, I'd say, you know, 7 plus or minus 1 or 2 units. But other than that, there wouldn't be any issues. Like anything like hydrogen peroxide would be fine. But we just need to make sure that there's, you know, geochemical issues with the bacteria.
Thanks, Mike. So just a couple of others, I'll just throw two at you at the same time here if you can split them up. But there's a question around potential byproducts from the bacterial treatment. Are there, what are they and where, what happens to them? And then just a separate question, which you might be able to tack on the back, is have you done any horizontal application, like horizontal well application with a treatment?
Well, from a byproduct standpoint, there's not really much that you're going to see. From the hydrocarbon side, no. When you get your compounds like benzene, they degrade into really unstable intermediates like catechol, and those are easily digested or easily broken down further. Really, I would say if you were gonna, it would be on. If you look at it's not really a byproduct, but if you look at the electron acceptors that we add, so we're adding nitrate, which is going to be reduced to nitrite at some point. Again, these are all temporary. One question that we do get quite a bit is on the sulfate end, because if you might have depending on geology, depending on the design, there's going to be a lot of variables. You may have a 250 to 1,000 milligram per liter plus concentration of sulfate in groundwater post injection, and so a lot of folks ask about hydrogen sulfide. We don't see it. It's something that we analyze for in our lab. Obvious vapor intrusion risk. If you're injecting this material, injecting a bunch of sulfate, you have sulfate reducing bacteria, or you're going to create a bunch of H2S. No, so I didn't get into it. That facultative blend of organisms that I referenced earlier, there's actually multiple bacteria in there. It's a blend, and there's one in there that's specific job was to deal with any hydrogen sulfide. We don't see it. I think personally, probably most of it complexes out in soils, but if any does persist in groundwater, it gets reduced to elemental sulfur actually. So I don't know, Duane, if you want to chime in there if there's
No, I
any
mean, it really is more on the side of the dissolved gases. I mean, you've got methane, which, I mean, you have methane in most of the hydrocarbon sites that you're dealing with today. In fact, when we add a lot of sulfate in the formation, we see a depression in the actual methane generation. I mean, you're going to get CO2, in your groundwater. So really, it's more on the dissolved gas side, of your overall degradation compounds related to the breakdown of your petroleum hydrocarbons by the bio.
And to the question about the horizontal wells, we really can't use wells like we sort of referenced earlier. I don't think well injections are suitable for most slurries. So carbon, ZVI, for example, you really can't use wells, whether they're vertical or horizontal, for applications of this technology. But horizontal wells, they've got typically long screens. It's hard to focus the injection. So some of these have really long, 30, 40, 50 meter screens on them. And it's really hard to focus sort of where that material goes. Now I know that there are folks working on that, but we haven't found a good application using horizontal wells yet.
Now I get this question asked by me by Jim Cummins with US EPA every time I see him, as have I come up with a methodology for applying our products using horizontal wells. And I keep telling him that we just haven't had the time to experiment with it, but it ultimately, I think, was going to be driven by packers. And, we apply, the products under pressure. So in most cases, horizontal wells are, use a drilling mud to be able to pull them into place. They break that mud and let the formation kind of, either collapse around them or whatever. So in most cases, if we apply something under pressure, it's going to want to follow the path of the horizontal well back to, you know, basically where it got installed. So whatever that methodology is, it's, you know, it's going to involve something of that nature where we can actually use packers to either pull through, you know, a grouted in well, or something in nature where we're actually pulling packer string through, you know, the grout itself or the mud itself that's been used to open up the horizontal pathway. So I guess to summarize, no, we have not applied it. There needs to be more work done on that to be able to apply, you know, these slurries under pressure in a horizontal setting.
Yeah, I guess just the one thing to add to that before we move on. We do quite a bit of angle injections. I know it's not the same thing, but we have created, you know, fabricated sort of, you know, feet for the geoprobe, angled feet for the geoprobe to sit on to be able to give us a constant angle. So underneath features, you know, roadways, buildings, creeks, those sorts of things. So no, not the same, but that is something that would be available.
Thanks, guys. One final question here just is, you know, is BOS 200 effective for a site where most wells have minor residual phase LNAPL following long-term multi-phase extraction?
It can be. It's going to depend on what that saturated soil looks like, and what the hydrocarbon fraction is. So, as I mentioned earlier, it really ties to the soil. LNAPL for us, you know, it's all about how much is that. What's that saturated soil look like? Is it 1,000, 2,000 milligrams per kilogram, or is it 10,000, 15,000? And so if we have that information, then we can say, you know, if you're in that one, you know, gave an upper limit of say maybe 3,000 or 4,000 milligrams per kilogram, that's where we feel comfortable. Once you go above that, we can't, you're looking at multiple applications. So that's sort of where maybe combined remedies come into play, but more than happy to evaluate it. And one other thing that kind of I hadn't mentioned, but kind of falls into that combined remedy realm is you're putting a lot of energy into the subsurface when you do one of these injections. And you sort of reshuffle the deck to a certain degree. And I have clients that will schedule on NAPL sites specifically, that'll schedule multi-phase extraction events post-injection. You're not going to pull the carbon out. And because you can get enhanced recovery post-injection. So if there is NAPL present, something that I would consider building into the scope would be to have some multi-phase events after we do the injection. So maybe let things settle for 2 to 4 weeks, come out, pull on those wells and see if you can pull anything out.
Yeah, I was going to say that, Mike. In fact, I was talking to a state regulator within the state of Tennessee in here in the U.S., and they had spent probably the last 10 years in their program predominantly doing multi-phase extraction with permanent systems. I mean, where they had, you know, where they were working actively, mechanically, you know, extracting on these sites, but they reached a plateau, and then we came in and you know, performed a characterization event to try to identify where the mass was still remaining after the extraction unit had worked for a long period of time. And after that, we came in and did a BOS 200 injection event. And so they now, a lot of these are sites that have extensive amount of LNAPL, and we're seeing, you know, reductions with the BOS 200, but they're just trying to speed up the process. So they're actually kicking those units back on and seeing, like Mike said, to where we've actually gone in and fractured the soils as a part of the overall injection methodology. And they're seeing, you know, increased recovery where the units had not, you know, been performing for a long period of time. So we're strong believers in you know, that combined approach, you know, and taking advantage of, you know, the energy that we put into the formation as a part of just the overall injection event itself. But you're also pulling oxygen into the formation that's, feeding terminal electron acceptors that, that help, continue to expedite the overall biological process that's occurring as part of the BOS 200 application.
Right. Yeah, just to kind of just tie one thing quick to that is that same thing goes with air sparge systems too. So I've worked on projects where we've turned the systems off, done an application, and then kicked those systems on to be able to provide supplemental oxygen. So those systems are in place. There's a possibility as well for this technology.
Thanks very much, Mike and Duane. So we're kind of getting really close to the end of the time allocated. I mean, I'm happy for you to kick on with to burn through these case studies. Obviously if people have time to stay on, they can. So yeah, we'll just get through to the end from now.
Yeah, we can get through these quickly. We kind of kept them brief because we kind of figured that we might be in this situation. Everything here that we're going to present is a project summary that's on our website. And so you can check that out or email Matt and he can get a hold of me and we can go ahead and get these for you. Or if there's something specific that you're looking for, specific geology or contaminant or situation, please let us know. We've probably got a summary written up for it. So we'll go ahead and move on. So this is a pre-drill site. This is a reactive barrier wall. It's got a couple of different things going on. It's up in the Northeast United States, and they brought this. This is a rest stop on the interstate, and they brought this area up to grade when they were building the interstate with all the blast rubble and debris from building the interstate. So very direct push was not an option. A lot of boulders and cobbles, and so you'll see here each of these well completions that you see was pre-drilled down to bedrock, and then AST came out, and this is our guy. These are our guys out there. Now then they're pushing direct push down through that bentonite and injecting top down to competent rock. And so we did a pilot test, and we did 2 phases of full scale. It was about 6 meters of construction debris. And then these are all of our injection points that you'll see here. These were all advanced with sonic. There's a wetlands that sits up here to the north, and groundwater flows in this direction. So, and this is our up gradient well, kind of close to the source. Here's our down gradient well. This well here was our pilot test well. It got kind of consumed by the full scale PRB design, so that got shifted after we did the injection event down gradient a little bit to give us a more accurate sampling location, since it wouldn't be actually within the barrier itself. So the barrier is about 50 meters long, about 88 injection points on 2¼ meter spacing. The injection interval varied quite a bit, depending on, because that bedrock interface varied quite a bit along this barrier length. So it's 10 to 17 meters, so it was quite a good span. PRB data is easy to interpret, especially when you've got 2 monitoring wells. What's coming in, what's coming out. The blue is total BTEX coming into the PRB. So on average, probably about 1,000 parts per billion coming into this barrier. And the orange is that down gradient well. So here between these 2 vertical lines, this was that pilot test. So we were using that MW205 that I referenced earlier. That well was abandoned after we did the injection event. MW207 was installed. So everything to the right of this line in orange was what's coming out. These really a lot of these are detection limits just added up. You'll see that there are a couple inflections, and so you see right here there's a small inflection corresponds with this high groundwater flux event. So as groundwater flux changes, we do our best to design it on the worst case. And there was a small inflection. It did come back down, and we're really more or less non-detect coming out the downside of this barrier. And we're about 2,000 days into this particular project, and This site has some natural sulfate fluxing through this zone. And so when I talked about, coming back and doing supplemental applications, we haven't had to do that on this particular project yet, but we may have to at some point. Here's a small UST site. So I wanted to throw one of these in. This is our average site. This is probably a little bit on the smaller side, but this is just a small corner gas station. We went out and did some supplemental sampling out there. These red PB borings that you see here, we try to supplement the existing network. And so we collected 40 soil samples from 2 to 6 meters, and all those samples came to RPI. We modified the design. The geology, we had this sandy silt over top of this highly decomposed granite. This was very highly weathered. We were able to direct push into this. The reason why I show this is we theorized that most of the mass was going to be sitting at this interface, and we collected our soil samples. So at each of these depth marks, we collected a soil sample, and really we only had soil hits at this one interval. So that's really the power of doing this high density sampling, if you can swing it on your project, because it really helps us dial in where we need to put the material, and we can discount other areas. So here's what the design ultimately looked like. So we took all that information, distilled it down into 3 different treatment areas. I wanted to give you an idea of sort of what a design looks like, what kind of weight, what kind of mass, what kind of volumes we're talking about. So that red area where the former UST was, it was about 60 square meters. We used 12 injection points on a 2¼ meter spacing, and we broke it down into shallow and deep zones, again based on that soil data. I did show you that. Go back one. All the mass was here, but groundwater did sit up here. The historic groundwater high did extend up into this region. So we did want to put some material there, but it was a relatively low loading, just to deal with, again, it's just one sampling point. We want to make sure we were covered. But this deeper zone is what really straddled that that highly contaminated interval that was at that interface between the sandy silt and the decomposed granite. And so you'll notice here's our shallow BOS loading per interval. And this is about every ½ meter or so. And you'll see how that increases significantly in that lower interval. We also add supplemental calcium sulfate or gypsum. And if you see a design from us, you may see that as a component. Gypsum is a relatively cheap, sparingly soluble sulfate source. And so it's going to bleed out sulfate over time. And so when we do our calculations for these sites, we're looking at individual constituents, as I mentioned earlier. So we're looking at your benzene, we're looking at the total hydrocarbons, but then we're also doing an electron acceptor balance. It's making sure we've got enough electron acceptors to be able to fuel the full process. And so to give you an idea we're injecting about 100 liters every ½ meter or so with depth. And we can probably wrap up with this, Matt. I do have one more, but we can go ahead and wrap up here and see if there are any additional questions. I like this slide a lot because it talks about, or it tells me that activated carbon has a finite capacity, right? So we talked about that before. And so there are upper limits. So we can only inject so much activated carbon. It's an economics issue, but it's also just we can only physically apply so much slurry to the subsurface. And so you see a couple different things. So these wells here, this grouping that you see where we're looking at, this is in micrograms per liter. So, between 1 and 2 generally. 1,000 micrograms per liter, excuse me. There's enough activated carbon to be able to adsorb that material easily. Now it's a matter of how much is in that sorb phase that's going to back diffuse. In this area here, I don't show it, but there wasn't a tremendous amount of saturated soil mass. This area, though, which is where the former dispensers were, we had 6-7 parts per million benzene in groundwater, much higher concentrations in soil. You can see that we did have an influence initially, but it's a different signature. These drop down to very low levels from this 1 to 2 ppm mark. Once you're up into this range, you're going to see this initial reduction. But again, this is just the sorption phase. Then you see the bacteria kick in and you see this nice first order logarithmic degradation, which is what biodegradation typically is going to follow, to the point where the span of, say, 6 months after we did the injection, this well caught up to the others. And that's mirrored in our TVPH, or our gasoline range organics as well. We see these higher concentration for this well, we see it drop, and then it's a nice slow decline to where it meets the others. Now this was this was in state of California, which has a low threat risk-based closure policy. This fell under that. And so after 4 quarters of reduced concentrations, they were able to close the site out. So, Matt, I know we're over time, so I guess we'll go ahead and wrap up. If anyone's got any additional questions, throw them in the chat, or please feel free to follow up with me or with Matt afterwards, and we can go ahead and get your responses. So I'll wrap up. Thank you very much for all your time.